Hello guys, Max here from Period 6, and today I'll be showing everyone how to solve number 5 on the 2018 AP Chemistry exam. And so the topics on this exam, on this question, acids and bases, trends relating to acid strength, percent dissociation, and Le Chatelier's principle. So that being said, let's get into the question. So the ionization of hydrogen fluoride is represented by the equation above. In a 0.035 molarity solution, the percent ionization is 13%. So, for part A, we're given two representations of the ionization of HF, and we have to explain why figure 1 is more accurate than figure 2. See, only one HF ionizes in figure 1. And all the rest remain as hydrogen fluorides, whereas in figure 2, everything ionizes. 100% ionization. Whereas here, it's only 1 in 8. So really, this question is actually simple. We don't need to know at all about the properties of hydrogen fluoride and whether or not it's a strong or weak acid, or whether it likes to dissociate or not, because we've already been given the percent ionization. It's 13%, which is closer to 13. 1 in 8 or 100%. That's what I thought. Figure 1 is obviously the correct choice. So, let's get into the correct explanations that would gain you credit for this. So you could say HF is a weak acid. This is consistent with figure 1, which shows 1 out of 8 HFs ionized. Or you could just say figure 2 is inaccurate because it shows 100% ionization. So just now going into the point distribution, this is the part A is a 1-point question. You get +1 for either explanation. So before we move on to part B, I'd just like to explore why. Why does HF have a low percent ionization? So, and we did learn this in class, so I think it's important to touch on this. So for halides bonded to hydrogen, as we go down the table, Ka tends to increase. And the reasoning behind this is because as the bond gets longer, the hydrogen ion can easily leave and drift away and form hydronium. And as we know, fluorine is at the top, meaning it will have the smallest bond distance to hydrogen. So it's not easy for it to let go. Okay, now let's move on to part B. Part B asks us to use the percent ionization data above to calculate the value of Ka for HF. Okay, so let's write out our Ka expression. Ka equals H3O plus F minus over HF, and we don't include water because we only include the aqueous things in the reaction. And since we're AP chemists, we really don't need to do rice charts, Let's just get our values in there. Ka equals 0.035 minus x over x squared. Now we're at a bit of a crossroads. What do we do now? How do we get the X concentration? Well, the X concentration is concentration of fluoride ions, the concentration of hydronium ions. And since we have the percent ionization, we can just go from there. So we know 0.13 equals H3O plus over the HF concentration, which is 0.035 molar. Doing some basic math, and this is the short response part. So we do not need to worry about any mental math that is in the past. We are living our best lives right now. So we get H3O plus equals 0.0455 molar. And since this isn't a lab question, we don't really need to worry about sig figs right now, which I know we're all happy about that. So now that we have H3O plus concentration, we in turn have the fluoride concentration. So let's just plug this back into the equation. I'm gonna actually write this in sig fig scientific notation. Sorry, excuse me. So 4.55 times 10 to the -3 squared divided by 0.035 minus 0.00455. And what does that give us? Ka comes out to 6.81 times 10 to the -4th. Alrighty. There we go. Part B, done. Well, before we move on to part C, let's just review the point distribution. How does the AP give points? Well, so +1 for this correct answer. And you also need +1 for getting the hydronium concentration, or I guess you could have solved for the fluoride ion concentration. And since we assume they're equal, it's the same thing. So, and of course, there's no units for the Ka, so this is the correct answer. What a nice question. So for part C, we have to figure out what would happen if 50 ml if distilled water is added to 50 ml of 0.035 molar HF, and what would happen to the percent ionization? Would it increase, decrease, or remain the same? And we have to justify with the calculation. Well, since we doubled the liters, the solution, the molarity will be halved. So actually, if we were in O'Malley's classroom right now, we would already know the answer to this question. We know that as the molarity decreases, the percent dissociation would increase. But unfortunately, not everyone, has such intuitive skills. Not everyone had the opportunity to take this class. So for the AP exam, we're gonna need to show a little more work. And actually, they say justify with an explanation or a calculation. So we're gonna actually do both. Starting off with the explanation, building off what I already wrote. So for the explanation portion, we are going to use Q. And the molarity will be halved. So we're looking at Q at the initial point, right where the reaction starts. So we know it's going to be 1/2 the concentration of H3O plus times 1/2 the concentration of F minus over 1/2 HF. With all those 1/2s, what do we eventually get? We eventually get 1/2 H3O plus F minus over HF. Wait a minute, this seems really similar. Where did we see this before? Oh, in part B, at our Ka expression. Look at that, so we get Q equals 1/2 Ka. If Q equals 1/2 Ka, then obviously Q is less than Ka. If Q is less than Ka, employing Le Chatelier's, oh, so fun to say, but I forget to spell. The reaction will shift to the left, to the right, as Q is less than K, and thus more product will be formed. This in turn increases percent ionization. There we go. So I ran out of space. I'm trying to solve it the other way. So now I'm going to explain how to solve part C numerically using the calculation method. So as we said before, there's a new volume. The volume is doubled. So molarity is halved. Concentration of HF equals 0.035 molarity over 2 equals 0.0175 molarity. So what are we going to do now? We're going to plug in to our Ka equation that we used in part B. 6 point, well, let's not use the exact number right yet. Ka equals x squared over 0.0175 minus x. And then the weird thing about this problem is that in part B, we did not assume that x was negligible. We assumed that, it affected the percent ionization outcome. But what the AP lets us do now, because, they're very nice, they let us assume that x is negligible, that because it doesn't fully dissociate, the amount of product formed will not really have an effect. And in doing so, they don't make us solve a complicated quadratic, which is very nice. So, thank you, AP officials. So we can actually just simplify this into x squared over 0.0175. So plugging that into what we got for part B, 6.81 times 10 to the negative 6, 10 to the fourth, equals x squared over 0.0175. We can pull out our calculators again, because remember, no ban on calculators for the short response. Then we get x equals 0.00345 molar. So, and then how do we find the percent ionization from this? Well, so now that we have the molarity for hydronium, we just need to plug that into the percent ionization formula. So it's going to be 0.00345 divided by our original HF concentration, which is 0.0175, and then times 100 to get a percent, obviously, and that'll be 20%. And what we need to compare this to something to see if it increased, right? Luckily, beginning of the question, they tell us the percent ionization is 13. Well, 20% is greater than 13%. Thus, percent ionization, increased. And part C is actually only worth 1 point. So You get 1 point for the correct answer and explanation. So correct answer, increased. Yeah, numbers are correct. And looking back at the other way of solving it, also +1, increases, all correct reasoning. And that's all. That's all I have for today, guys. I hope everyone is safe and doing well, and good luck on the upcoming AP exam.